Okay, so at this point, we've discussed how quantization lowers the memory requirements for a neural network, why that matters, and we know that's because neural networks can take up a lot of memory, especially the modern day ones that are in the billions of parameters. We even discussed, what it really means to lower the precision of a particular number in memory. We saw examples of how we took a number and represented it in different precisions and casted it to different data types. And we learned what those data types are, what it means for a data type to be signed and unsigned. And then we finally took all that knowledge and we tried to cast a number, negative 128.1, to an int8 data type. And it failed, it threw an error. And we said that's because it's outside the range supported by an int8 data type in PyTorch and in the computer. And so in this video, I want to build some intuition around how linear quantization works. And I'm going to show you how we can, constrain the range of a list of numbers so that we can actually cast them to a target data type without losing their relative distance between each other. We want to maintain that, and I'm going to explain that in this video. So linear quantization is the solution to this problem. It has done very, very well when quantizing numbers to a smaller data type with lower precision. Now, so I want you, before we go into any calculations, I want to gain this intuition around why we call it linear quantization and what it does. So let's imagine a scenario where we have this list of three 32-bit numbers and we want to cast them and represent them in an int8 data type so that we can save 3 bytes per number because they're 4 bytes at 32-bit, and then we're moving them down to int8, which is only 1 byte or 8 bits. And now linear quantization, what it's going to do is it's going to take these numbers, right, and then it's going to change them such that they are not the numbers that they were before, but the values that they were before, but they're now values that are within the range of negative 128 or 127. And so let's just say that this number right here is negative 500, and you'll see that in our example here soon. Let's just say this number is negative 500, and we want to cast it to int8. Well, the most negative number that int8 can support is negative 128, and so we first have to change this number so that it fits within the range of negative 128 to 127. And let's just say that it moves it right here, and let's just say that this right here is negative 128, which is actually what would happen. And so now we can, because we changed negative 500 into negative 128, we now can cast it to an int8 data type because that's supported by the int8 data type. And then we do that same thing to all of these. And now we're not randomly just casting these to numbers that are within this range. When we cast these numbers from 32-bit up here to 8-bit, we need to maintain, and this is where the linear aspect of this comes in, we need to maintain the relative distance between the numbers. And what I mean by that, if we go to, I'm going to draw this up on a board real quick. So I'm on this board real quick. I want to draw this up. The whole point of linear quantization is to maintain these relative distances. And what I mean by that is that let's just take these two numbers right here. They are this far apart in the 32-bit space, right? And this is the total range of the numbers in the 32-bit array, right? This is the minimum number, this is the maximum number, and this is how far apart these numbers are. If I was to take how far apart these are right here in terms of absolute value, and then divide it by how big the range is up here, and let's just say that these take up, I'm gonna say 60% of that range. That this is 60% of the total range up here. Well, when we cast them down, they now have this distance, right? And this is the total range of all of these numbers right here. This is how far apart they are. It's literally 127 minus negative 128. And they here in this int8 domain, if you should say, should be approximately 60% of the range of values here. So the distance between these two, if there's 60% of the total range between the minimum and maximum value, if their distance is 60% of that, then their distance should be approximately 60% of the distance here when it's quantized. When we change the numbers and we cast them down to int 8, their distance should be 60% of the total range here as well. And that is what I mean by relative distance between values. And that is what we mean by linear. And that whole property right there is super, super important. And to the extent that these two numbers, the 60% here, and I said approximately 60% here, to the extent that these two numbers are the same is to the extent that our quantization algorithm was of quality and that it did its job and it was accurate. If these two numbers are way off, then we have what's called quantization error, and that happens all the time. And our job as algorithm designers is to make sure that that quantization error is as low as possible. And so, because if it's really high and we do our calculations and our matrix multiplication in our neural network, and this relative distance right here is way off, right, then we're going to get outputs and predictions and model performance that's way off from the original, and that's not what we want. We want to preserve as much performance as possible. And so if you find a quantized model that is in a lower precision, let's just say 8-bit, and it's not performing that well, or as well as the original 32-bit model, you now know that this is the reason why it is not performing as well. And I think that's very powerful for you to have that under the hood intuitive understanding of quantization. Now we're going to move from an intuitive explanation to actually doing some math. We're going to go through the formulas and we're going to quantize a list of values on our own.